All right, today we're talking about the nervous system. Let's get right into it and see if we can cover this material in a short amount of time here. So, I just have, just to start us off, I have this, whoops, I have a diagram right here showing the breakdown of the nervous system. So, the nervous system is broken down, or can be divided into two components here. We have the central nervous system, made up of the brain and the spinal cord, and then we have our peripheral nervous system, and that can be broken up into our autonomic nervous system and our somatic nervous system. Now, the somatic nervous system is comprised of sensory and motor nerves, and then our autonomic nervous system, which is over here, and this is really what we're going to be focusing on today, is comprised of our sympathetic nervous system and our parasympathetic nervous system. So, to get started, I want to come down here and I just want to talk about these points, right? So, points of origin, number of neurons in each pathway, location of ganglia, neurotransmitters, receptor types, and action. So we'll get into all of that. That's what we're going to be talking about. But to get us started, I just want to start with something that I feel like really helped me. I'm just going to draw a neuron, right? So we have our cell body, and we have our axon, and that's leading to our synapse here. And this is what we would call a neuron. And so when we talk about a nerve, we're talking about multiple neurons put together, and that's creating a nerve. But what I want to show is the pathway of these neurons in the body, or these nerves. So let's see. Let's get started by just drawing a spinal cord right here. Okay. And I'm going to blow this up just a little bit so you can see spinal cord here like this. If you'll remember from anatomy, we have our ventral and dorsal roots and our lateral horns on the sides here of the spinal cord. And that is where these cell bodies are going to be originating, is the lateral horn of the spinal cord. So that's our point of origin. Now, along our spinal column, on either side, we have what we call the sympathetic chain ganglia, which is plural. And these are typically synapse sites for neurons, as we'll get into here in just a second. So I'm going to draw one on this side too. Actually, this is what I'll do. This will be faster. Let's do this. One right here. There we go. All right. And then I'm going to just draw some lungs here. And I'm going to put a heart right here. And let's see. I'm going to put like a liver right here. Put stomach. And we'll throw a kidney in right here. And we will put an adrenal medulla right here on the kidney. And I'll throw in large intestine here. And then we have our Small intestines here. All right. And I'm just going to draw a spinal cord over here as well. There we go, spinal cord right there. All right, this is just going to be a little bit of a map to help us understand the pathways of the neurons into sympathetic and the parasympathetic nervous systems. So to get started, I'm going to show our sympathetic nerves or neurons and the pathway that they follow. So we have our point of origin, as we discussed, in the lateral horn of the spinal cord. And I'm going to draw my axon here, and it's going to be coming to the sympathetic chain ganglion. Let me zoom in just a little bit. And this will be a synapse site. And I'll just draw another one on this side. Axon coming here, synapse. And notice that these axons here are myelinated. I don't think I spelled that right. Myelinated. Oh goodness, there we go. And once they synapse, our sympathetic neurons, when they synapse in the sympathetic chain ganglia, there's another cell body. So this is what we would call right here, these ones from the spinal cord of the sympathetic chain ganglia are preganglionic neurons. And then we have our postganglionic neurons. So in these nerves, there's two sets of neurons in this pathway. Here would be our postganglionic neuron. And I'm going to draw another one on this side, like this. Boom. All right. So you'll notice with the sympathetic nervous system, we have a short preganglionic neuron and a longer postganglionic neuron. And the postganglionic neuron is unmyelinated. And these postganglionic neurons will then synapse on cardiac muscle, smooth muscle, and glands in the body. And these are, again, our sympathetic nerves. So these are going to be involved in these categories. Cardiac muscle, obviously found in the heart. Smooth muscle could be found in blood vessels, could be found in organs in the abdominal cavity, for example, erector pili. And then we have our glands, for example, sweat glands, adrenal glands, and so forth. So our sympathetic nerves are going to synapse at those places. Let's see. And those organs or muscle, whatever it may be that it's synapsing at, is known as an effector that is generating a response. Now, in the sympathetic nervous system, we have our sympathetic nerves. We also have splanchnic nerves. And the splanchnic nerves are a little bit different because we're going to add here another ganglion that's further from the vertebral column, but this is going to be called a collateral ganglion. And these collateral ganglia, like I said, are further away from the spinal cord. And I'm going to show that here with a cell body originating here. And with these neurons, they will, our preganglionic neuron will pass through the sympathetic chain ganglia, but it will not synapse there. It will actually continue, and it will synapse in the collateral ganglion. And from there, we will have our postganglionic neuron that will continue into a cavity in the abdominopelvic region to synapse on muscles there. For example, the colon, the small intestines, the stomach, etc. And those are our splanchnic nerves. Like so. All right. We also have a nerve that goes, that's known as that travels through the adrenal medulla pathway, and that nerve is going to begin again in the lateral horn of the spinal cord. It will pass through the sympathetic chain ganglia, but not synapse in that location. It will also pass through the collateral ganglia, but not synapse there either. It will actually continue on and synapse on the adrenal medulla of the kidney. So notice that there's only one neuron there. There's not a set of a pre and post ganglionic. There's just one neuron that travels all the way and is myelinated. So those are some nerves, nerve pathways of the sympathetic nervous system. Now we also have our parasympathetic nervous system. And specifically, these are found originating in the cranial or sacral regions of the spinal cord. And we want to give specific attention to what we call the vagus nerve, which is back that up. Cranial nerve 10. And this nerve accounts for 75% of the parasympathetic nervous system. And will also originate in the lateral horn of the spinal cord. And these nerves are going to have the opposite orientation of the sympathetic nerves. So sympathetic nerves are made of a short preganglionic neuron and a long postganglionic neuron. But the parasympathetic will be a long preganglionic neuron, which will then synapse on a short postganglionic neuron, and those will go to effector organs that are in the abdominal cavity, abdominal sacral cavity. So something I forgot to mention is that when we're talking about the sympathetic nervous system, we're talking about fight or flight responses in the body. Whereas parasympathetic nervous system and nerves, we're talking about rest and digest. And so it makes sense that the parasympathetic nerves would travel to your abdominal cavity where you have a lot of digestive organs and your sympathetic nerves would travel to your thoracic cavity and to your skin, because in your thoracic cavity is where you have your heart and lungs that would be crucial and essential in your ability to survive in stressful situations. So now that we have had some time to look at the pathways of these nerves, the sympathetic nerves, splanchnic nerves in the sympathetic nervous system, and then the parasympathetic nerves in the parasympathetic nervous system, I want to take some time to look a little bit more closely at these neurons and how they operate. And so we're going to look at neurotransmitters that are released from these neurons, receptor types that respond to those neurotransmitters, etc. So for our sympathetic nervous system, there's a few pathways here that we'll look at again. So one of them will be a neuron that is going to release neurotransmitters at the synaptic cleft known as acetylcholine. I'm going to abbreviate that as ACH here. And when those neurotransmitters, right, we've gone through an action potential and it's caused the release of acetylcholine through these vesicles that will adhere to the membrane and release into the synaptic cleft, then you have your cell body of your next neuron that has receptors on the membrane that are known as nicotinic 2 receptors. I'm going to abbreviate as N2. And these receptors will respond to the acetylcholine and cause another action potential that will result in the release of another neurotransmitter of at the terminal end of the postganglionic neuron. And these neurotransmitters are called norepinephrine, and I'm going to abbreviate that as NE, found here. And those neurotransmitters will be released onto an effector target that has a number of different receptors that will respond to norepinephrine. So they could have alpha-1 receptors, alpha-2 receptors, beta-1 receptors, beta-2 receptors, or beta-3 receptors. Those are receptor types that will respond to norepinephrine. And we'll talk about receptor types a little bit here more in a second. And so the target effectors here we're looking at would be things like, again, cardiac muscle, smooth muscle, and glands. So those receptors respond to norepinephrine and cause a response in those target effectors. We'll talk a little bit more about that too as well in just a moment. Another pathway here is in the sympathetic nervous system is a neuron that will release neurotransmitters that are acetylcholine. Surprise, surprise. We have those again. But this time, even though our cell body still has N2 receptors that are responding to acetylcholine, this pathway will result in the release of more acetylcholine instead of norepinephrine. And the receptors that will respond to this acetylcholine on this target effector will be muscarinic 1 receptors, or M1. And that is going to specifically be associated with the generalized sweat glands throughout the body. So this is going to increase sweating. Also wanted to point out our adrenal medulla pathway here, where we have a neuron that travels all the way to the adrenal medulla. Whoops, let me make that a little bit more straight, shall we? And at the terminal end of that neuron, we will have a neurotransmitters released. Take a wild guess at what those are. You got it right. Acetylcholine. Wait a second. Okay, I just second guessed myself there for a second, but yes, we have acetylcholine, and that will be synapsing directly on the adrenal medulla, which I'm just going to abbreviate as AM, adrenal medulla. And that will result in a release of further neurotransmitters into the bloodstream. And those neurotransmitters are known as epinephrine. Now I want to take a moment to talk a little bit about the parasympathetic nervous system. And we just have one pathway here we're going to look at with a neuron that will synapse with another neuron. Again, we have our neurotransmitter being released, acetylcholine. We have our receptor to acetylcholine, nicotinic 2. And we have our postganglionic neuron releasing neurotransmitters, acetylcholine. Again. And that will go to the target effectors, whatever they may be. Again, this pathway is associated with rest and digest, and we're going to have receptors on those target effectors. That could be muscarinic 1, 2, 3, 4, or 5. So those are some pathways of neurons in both the sympathetic nervous system and the parasympathetic nervous system. Now, why is that important? Well, that will take us into looking at different types of receptors. And so just kind of keep in mind what we've gone over here as we talk about these different types of receptors. So we have, sorry about the background music. I have an awesome family and they're having a good time upstairs. But let's focus back on these receptors for a second. So there's two broad categories that we're going to look at here. One is cholinergic receptors. The other is adrenergic receptors. Now, cholinergic receptors are receptors that are going to respond to the neurotransmitter acetylcholine. And these are our nicotinic receptors. So you remember N2, like we discussed up here, right, with these ones. And our muscarinic receptors. So again, M1, M2, M3, M4, and M5. Those are our different types of cholinergic receptors that respond to acetylcholine. Then we have our adrenergic receptors that respond to norepinephrine. which again is our neurotransmitter that we discussed here. And those receptors are going to be alpha 1, alpha 2, beta 1, beta 2, and beta 3. Now, why are these receptors important? What do they do? Why do we care about them at all? Well, it's just important to know that when we have acetylcholine being released from our preganglionic neuron, the protein receptors that are responding to that and causing an action potential, resulting in an action potential to travel down the postganglionic neuron, that's our N2 receptors that are doing that. Now, what about these other ones? Well, let's talk about some potential effector organs. So, for example, if we had the eye, we're going to look at an eye. We have a muscle in the eye, in the iris of the eye, that moves in kind of a circular motion. So when it constricts, that muscle is going to pull in like this towards itself. Okay, keep that in mind. We also have muscles that are traveling towards the outside of the iris, like so. When they constrict, they're going to pull the opposite direction, which is going to cause these muscles to expand, which would be the dilation of the iris. Now, what receptors enable that to happen? Well, in the iris, we have M3 receptors on this circular muscle here, and we have alpha 1 receptors for these muscles here. Draw this like this. Here we go. All right, so if we have the release of acetylcholine, remember that muscarinic 3 receptors are cholinergic receptors which respond to acetylcholine. So if we have a greater amount of acetylcholine than other neurotransmitters, then we're going to get the response of this circular muscle constricting. And so it's going to pull in, and it's going to look something more like this. So your iris, the pupil of the eye, is going to become smaller, right? And that will be in the rest and digest state. That's the parasympathetic nervous response. Now, if we have norepinephrine that's being released as a neurotransmitter, then in greater amounts, then what's going to respond is the adrenergic receptor A1, and that is going to cause the eye to dilate as a sympathetic nervous system response. Let's look at another effector organ, the heart. I wonder if I can do this. Oh yeah, there we go. All right, so we have 2 different types of receptors on the cells of cardiac muscle. We have M2 and we have beta 1. Now remember, M2 is going to respond to acetylcholine. And it's going to be associated with the parasympathetic nervous system, because in the parasympathetic nervous system, we have 2 synapses that are releasing acetylcholine. And the receptors on our effector targets, our target effectors, are muscarinic. And so if we have an M2 receptor responding to acetylcholine, what's that going to do to the heart rate? What's it going to cause? It's going to cause the heart rate to decrease. On the other hand, if we have norepinephrine being released, the receptor in the sympathetic nervous system, seen here, that is going to respond is beta 1. What will that do to the heart rate? Well, fight or flight, stressed, trying to survive, body's going to increase heart rate. We look at the lungs. Our lungs are the opposite of the heart, so we have muscarinic 1, beta 2. Muscarinic 1 are going to cause dilation of bronchioles, so greater airflow can pass through. So when you're running away from something, flight, right, or fighting something, you have more oxygen available in your body. Whereas beta 2 would cause constriction of the bronchioles because you don't need as much airflow in that situation. If we look at blood vessels, we draw it like this. Blood vessels can have alpha 1 receptors that will cause the blood vessels to dilate, increase the amount of blood flow going through the blood vessels. So those are how those receptors work. That's why they're important. And another thing that we should note here before we end is that we want to think about cyclic AMP. Cyclic AMP, when cyclic AMP increases, let me draw it like this. When cyclic AMP increases, that is going to result in a greater sympathetic response. When cyclic AMP decreases, it's going to result in a greater parasympathetic response. So when we look at these receptors, M1, M3, M5, and alpha 1 are all not actually going to be associated with a change in CAMP necessarily, but actually an increase in IP3, which will affect our G proteins, which will increase amounts of calcium inside the cell, which of course will have different effects that are significant. If we look at M2, M4, and alpha 2 receptors, now we're looking at a decrease of cyclic AMP, which makes sense because these muscarinic receptors often are associated with parasympathetic nervous system. So if we have a decrease in CAMP, what did we say? Increased parasympathetic response. We also have our beta 1, beta 2, and beta 3 receptors that will result in the increase cyclic AMP, which makes sense because they are associated here with the sympathetic nervous system. So there you have it. We've discussed the sympathetic, parasympathetic nervous systems, differences between them, receptors that are involved, and how they can impact different organs or target effectors in the body. And the only other thing I'll mention real quick is the somatic nervous system. Won't go as in depth, but just want to briefly mention that the somatic nervous system, again, is made of the sensory and motor nerves or nervous systems. And those are going to originate in the ventral and dorsal roots or horns of the spinal cord. And those, the somatic nervous system is made of nerves that we can consciously control, things that we think about. So if I want to, draw this star, I need to move my hand in certain directions. I'm thinking about it, and so that's causing I'm able to actually consciously make it happen. If I want to put my hands together and clap, I'm thinking about it. I'm causing it to happen. Whereas autonomic are things like my heart rate and digestion that are happening that I don't have to think about in order for them to take place and happen. So those are just some of the differences there. Hope you enjoyed the video. If you have any feedback for me, things I could improve, maybe focus on explaining a little better, I'd love to hear it. Thanks so much for your time.